Let's start by knowing what we are going to discuss in this section. We will have a clear definition of process safety management. We will know the differences between personal safety and process safety. We will look through also the origin and evolution of process safety management, who are the caretakers of the process safety management, and also we will know the scope of implementation and exemption for this PSM standard or the process safety management standard. Okay, so let's start by defining what is process safety. Many definitions you will find throughout many organizations, but there is somehow a shared point between all of these definitions. The true meaning or the true definition of process safety is a disciplined framework for managing the integrity of operating systems and processes handling hazardous substances by applying good design principles, engineering and operating and maintenance practices. So, your true meaning of or your true definition of process safety is to manage the integrity. The integrity is the prevention of major accidents by applying sound mechanical design and good engineering practices. Okay? So now we want to know what are the key differences between personal, which is occupational safety, and process safety. In this table you'll find 10 points of differences between process safety and occupational safety. We will discuss them respectively. Number one, we want to know the frequency of incidents. If you see the frequency of incidents relevant to process safety, they will be lower. If you look through the incidents relevant to process safety, like Piper Alpha or British Petroleum Horizon, you'll find that these incidents are not the everyday event or just like any occupational injury or any occupational illness. However, if you see the consequences or the consequence of the incidents relevant to process safety, it will be catastrophic. So, low probability and very, very high severity. You will find this in contrast with the occupational safety. As you can see, the frequency of incidents is much higher and also the consequence of incidents is lower. So now we're talking about the target. What is the target of process safety and what is the target of occupational safety? From the definition, you will see that the process safety's target is to prevent the unintentional release of chemicals, while occupational safety's target is to prevent the workplace hazards. I think the difference between both of the targets are very significant. Okay, moving on to the umbrella. The process safety protects everyone, while occupational safety doesn't. It only focuses on the workforce. Okay? Now, about the consideration issue. We will see that process safety considers human, environment, and business, while occupational safety focuses only on humans. Okay, what about the focus? I believe that process safety focuses to change the system design level, while occupational safety focuses to change the human behavior. Moving on to the next item, what is the expense of implementation? The expense of implementation of process safety management is much higher in comparison with occupational safety. Moreover, the complexity of comprehension, how easily the process safety is understood, I think the complexity is much higher, and process safety is easily misunderstood and misinterpreted with other categories of safety in general. While occupational safety is easily understood, as you can see from the comparison points, it only focuses on prevention of workplace hazards and to change the human behavior. So what about the end result or the end purpose of process safety? I believe also from the definition that we can conclude that the major or the end purpose of process safety is to prevent major incidents, while occupational safety focuses to decrease the personnel injuries. And the last point, we will say that the needed level of support for implementation of process safety is higher, of course, than occupational safety, because process safety is a new trend. It cannot be easily communicated or endorsed by the management. This is a new stuff for them. They need to understand it well. That's why we are going to discuss the elements in detail. Specifically, you will find that the first element of process safety management as we move forward will be the employer involvement. So you'll get the idea that this trend needs a lot of support. Okay. Why should we have a process safety management in our organization? Why do you want to have this system? What is the importance or what is the significance of having this system in your organization? I believe we have three main categories. You will find a moral reason, you will find a legal reason, and we will find a financial reason. The moral reason, if you study or if you have looked through major disasters which happened in the past, like Piper Alpha or Deepwater Horizon, you will find that these incidents could have been prevented if only process safety measures were taken. You could have avoided all of these needless fatalities if only process safety management measures were applied. What about the legal reasons? I believe you might need to have this system in order to comply with legislation and meet your legal obligations. And at last, the financial reasons is to eliminate the catastrophic costs of process safety incidents. If you see the cost of an accident or an incident like Deepwater Horizon, you say that it costed more over than $62 billion. And we are talking about direct and indirect costs of this incident. Okay, moving on to the next slide. When did the PSM appear? On July 17, 1990, OSHA, or Occupational Safety and Health Administration in the United States of America, published in the Federal Register number 55 FR 29150 a proposed standard called the Process Safety Management of Highly Hazardous Chemicals. This proposed standard was enacted on 1994, and further amendments were done on 1992, 1996, 2012, and 2013. The standard contains requirements for the management of hazards associated with processes using highly hazardous chemicals to ensure or to help assure safe and healthful workplace. This standard has 14 elements. We will discuss them in rigorous details. Don't worry, you will know it all. We're just giving you the preface. So now we are going to talk about who are the caretakers of process safety. We have number 1, OSHA, which is the Occupational Safety and Health Administration in the United States. We have the CCPS, which is a Chemical Center of Process Safety, also in the United States. We have the IOGP, which is the International Association of Oil and Gas Producers. We have the API, the American Petroleum Institute, and then last we have the HSE, which is the Health and Safety Executive in the UK. Okay? Now we want to know what are the strategic approaches to process safety. Basically, we have 2 strategic approaches, which are the standard-based approach and the risk-based approach. This course mainly focuses on the standard-based approach. However, we are going to make some interrelations between the standard-based and risk-based approach. Anyhow, the standard-based approach entitles you to know what should you do. Okay, and this approach is adopted by OSHA. As you know, OSHA already published a standard. This standard covers all the elements of process safety management. While the risk-based approach is adopted by CCPS, and it entitles you to how better manage the risk. You know that already the risk-based approach is derived from the standard-based approach. However, there are some more variations that the risk-based approach already headed to, and we will also mention this along the pathway of the course. Okay, so now we're going to the standard-based approach. What is the scope of application of this standard? The PSM standard is 1910.119. We will know what is the scope of application. Okay. Number 1, this standard applies to a process which involves a specific chemical at or above the specified threshold quantities. Okay, now from this statement we have a definition of process, and also we want to know what are the threshold quantities. Okay, OSHA defines the process as any activity involving a highly hazardous chemical, including using, storing, manufacturing, handling, or moving such chemicals at the site, or any combination of these activities. Now you have already known the definition process. We want to know what is the threshold quantities and what is a highly hazardous chemical. The threshold quantities, it means that these quantities cannot be exceeded whatsoever, because if they are exceeded, then you are facing a hazard. Okay, you are facing a hazard. The hazard could be fire, it could be intoxication, it could be any other harmful event. Okay, and regarding the highly hazardous chemicals, already OSHA has released an appendix to this standard. This appendix contains 137 listed highly hazardous chemicals, and these chemicals already are stated in this appendix. You will see the threshold quantities mentioned clearly. So if you are doing a process which involves a highly hazardous chemical at or above the threshold quantities of that you will see in this appendix, then this standard applies to you. And I have already attached this appendix in the course resources, so you can check it to see the 137 listed chemicals, see their threshold quantities. If you want to know how to calculate the threshold quantities, you can just ask in the course discussion board, and we can solve some problems together. So, what else does this standard covers? It covers a process which involves a Category 1 flammable gas in a quantity of 10,000 pounds or more. What is a Category 1 flammable gas? According to OSHA 1910.1200 standard, the Category 1 flammable gas is a gas at standard temperature and pressure, 20 degrees centigrade and 14.7 psi, is ignitable when in mixture of 13% or less by volume in air, or have a flammable range with air of at least 12% regardless of the lower flammable limit. What are all of these heebie-jeebies? Let's find out more. What is the lower flammable limit, and what is the upper flammable limit, and what is the flammable range? The lower flammable limit, or lower explosive limit, is the lowest concentration range over which a flammable gas or vapor can be ignited at a given temperature and pressure. This is the lowest concentration that can give you a flammable or explosive mixture with air. Okay, and from the definition we see that they are talking about standard temperature and pressure, so we are talking about 20 degrees centigrade and 14.7 psi. Okay, let's take an example from this table. Let me just first use a laser pointer. Let's take methane. The lower explosive limit of methane is 5%, which means that you need only 5% by volume in air of methane gas to form a flammable or explosive mixture, okay, that can be ignited easily when given an ignition source. Okay, what about now the upper explosive or upper flammable limit? The upper explosive or upper flammable limit is the highest concentration at which the ignition can take place. Okay, so below the lower explosive limit, the mixture is too lean to combust. Okay, and above the upper explosive limit, it will be too rich to combust or give a combustion. So what lies between the lower explosive limit and upper explosive limit, or lower flammable limit and upper flammable limit, is called the flammability range. So as you can see from this table, there are some flammable gases, and I believe all of them are under the umbrella of category 1 flammable gas. Okay, moving on. And at last, what is the area of coverage for the PSM standard? The area of coverage for PSM standard involves, at last, a process which involves a flammable liquid with a flash point below 100 degrees Fahrenheit on site in one location in a quantity of 10,000 pounds or more. What is flash point? What is the definition of flash point? The flash point is the lowest temperature at which the flammable vapor of the material will ignite when given an ignition source. And this ignition will be of a flash fire, which means that this fire will not be continuous. If the ignition source is removed, the flash fire will cease. And please don't mix between the flash point and the fire point, as the fire point will give you a continuous fire, unstoppable, even if the ignition source is removed. And this is according to NFPA 30, the Code of Flammable and Combustible Liquids. Okay? So on the next slide, we'll see some flammable liquids which have a flash point of 37.8 degrees centigrade and below. You have here the acetone, minus 18, hexane, minus 7, pentane, minus 40, and so on. Now, let's talk about the scope of exemption. What are the areas that the PSM standard doesn't cover? The PSM standard doesn't apply to a process which involves a flammable liquid with a flash point below 100 degrees Fahrenheit on site in one location if the hydrocarbon fuels are used solely for workplace consumption as a fuel, as a pure fuel. If you have a warehouse and this warehouse uses this flammable liquid only as fuel, then this standard is not applied. B, if this flammable liquid is stored in an atmospheric tank or kept below the normal boiling point without benefit of chilling or refrigeration. Okay? The OSHA PSM doesn't apply also to retail facilities such as gasoline station. As you know, OSHA already released a retail exemption policy to exclude the retail facilities from the scope of PSM. Why is that? Quite frankly, it's pretty strange, but OSHA doesn't believe that highly hazardous chemicals would exist in such facility with such a quantity of 10,000 pounds or more. The OSHA PSM standard doesn't apply to oil and gas drilling or servicing operations, such as the platforms and workover rigs and so on. At last, the OSHA PSM standard doesn't apply to normally unoccupied remote facilities, such as the unmanned offshore platforms. And by definition, if you want to know the normally unoccupied facilities, it will be a facility at which is operated, maintained, or serviced by employees who visit the facility only periodically to check the operation and to perform necessary operating or maintenance tasks. No employees in these facilities are permanently stationed, okay? And this facility must be geographically remote in order to meet the requirements. So hello and welcome to module number 2 of the PSM course. This module is yet the most important one as it is the core of our course, so it will be the longest and the largest. Okay, so let's go directly to module number 2. Let's start. In this module, we will cover the following. We will know all OSHA PSM elements, the 14 elements of Process Safety Management Standard. We will know the interrelation between these elements together. And at last, we will know the differences between the standard-based and risk-based PSM approaches, which are basically the OSHA against the CCPS. So, let's start. What are the OSHA PSM elements? We have 14 elements, as you can see from this graph. It starts with the employee involvement. If you recall that when we talked about the employer involvement and the promotion of safety culture, we said that we will go to the first pillar of PSM standard, which is the employee involvement. And hence, they put it as the first pillar of PSM system. Number 2 will be the process safety information, followed by the process hazard analysis, operating procedure, training, contractors, pre-startup safety review, mechanical integrity, hot work, management of change, incident investigation, emergency planning and response, compliance audits, and at last, the trade secrets. These elements are somehow interrelated, but first we will study each individual element separately, and at the end of this module we will see the interrelation between these elements together. Okay, so let's start by the first element, the employee participation or involvement. also known as in the European school as safety leadership. OSHA mandates the following regarding this element. Number one, employers shall develop a written plan of action regarding employee participation, which means that this plan should include how the employees are going to participate in order to promote the health and safety culture or the process safety culture. Number two, employers shall consult with employees on the conduct and development of process hazard analyses and on the development of other elements of process safety management. Okay, so this paragraph entitles employers to consult with employees regarding the development of process hazard analyses and other elements of PSM. So basically this element defines how the employee shall participate in the development of PSM and how the employer himself should promote the process safety culture. So moving to the next slide, regardless of what OSHA mandates, we need to define the criteria of a healthy process safety leadership. So forget about the standard, we need to know what is the true meaning of a process safety leader. The criteria of a healthy process safety leadership consists of the following. Number one, hazard and risk awareness of process safety leadership. Number two, broad level visibility and promotion. Number three, definition of responsibilities. Number four, provision of adequate resources. Number five, setting the targets. And at last, commitment towards continuous improvement. So these are the criteria which define a healthy process safety leadership. And these criteria must be endorsed by managers and directors. We are going to discuss individual elements together and we shall see. Now we are going to talk about criteria or criterion number one, which is the hazard and risk awareness of PS leadership. Excuse me. History had shown that most of disasters which happen in the world are due to main three reasons. Number one is a lack of technical knowledge by management, which means that the management is over-focused to administrative stuff and neglected the technicalities. Number two will be the lack of information, lack of reporting, the reporting guidelines, the reporting guides, the reporting routes, to the management. And at last, which is the poor decision making and the underestimation of consequences of the decision, which means that sometimes management gets stuck with the technical staff doing some decisions or taking some decisions that may affect the integrity of the plant itself. And such decisions could be like delaying plant maintenance of an old plant or cutting the critical staff, which are the people who are irreplaceable by all means and cannot be expanded easily. Okay, so moving on. So leaders should be involved, competent, and actively engaged. And this doesn't happen by chance. No one just can brag about his experience as an evidence of competency, because competency is a huge world which contains the knowledge, the ability, the training, and experience. So now he is taking only one element and proves that he is competent enough. No, it's not competent enough. Okay? So now the leaders should be fully aware of the hazard and risk potential of their processing activities and potential consequences that their decisions of to do or not to do things may lead to. Okay? So now we're going to the criterion number two, which is the broad visibility, the broad level visibility and promotion of process safety. The managers and directors play a key role in the promotion of process safety culture. If you recall the comparison that we've made between the personnel safety or occupational safety and process safety, we said that process safety is easily misunderstood and requires a lot of support from the management and directors. That's why the managers here are playing a key role in the promotion of PS culture. They set the HSE tone, their actions are noted by the workers, and hence they should lead by example. And from here I recall something that most managers do is to just neglect the paperwork, or what they say, it's a paperwork. Just like, for example, if you take HAZOPs, if you are going to introduce new equipment in the plant or you are conducting a management of change and now you need to make a HAZOP review or a re-HAZOP, sometimes managers say there is no need to do so. While it's very critical to do it because it may identify something that wasn't seen before, managers just say, I have my original HAZOP. And this is reflected to the employees themselves. They will say to themselves, why should I care if the management doesn't? While on the contrary, if you take it that management or managers say, okay, we must do the HAZOP, it will create a feeling inside the employees that management does care and they already are involved in the technical stuff such as the HAZOPs. So in conclusion, the visibility of their actions will promote a healthy process safety culture. Okay, moving up to criterion number 3, definition of responsibilities. This criterion is considered as one of the most important criteria in the definition of a healthy process safety leadership, which means that all responsibilities must be clearly defined and clearly communicated to employees. Everyone should know what they have to do, and this must be entitled accurately. Okay, so everyone who plays a role in the PSM framework should be held accountable for their actions, regardless of their organizational level, without endorsing the individual blame culture. And if you take any trend of safety, just like the occupational safety or the functional safety or the process safety, you will see that no blame culture is the slogan of all of these trends. So you shouldn't endorse the blame culture in the process safety. Okay, moving up to the next criterion. The provision of adequate resources. As we say, or if you recall in the module number 1 of preface regarding the comparison, that process safety is more expensive. So I believe provision of adequate resources is a very important criterion in the definition of a healthy process and safety leadership. So the resources can be human, the right number of people who have the right skills and experience, financial, which may include the capital expenditure and operational budgets. And regarding this point also, we said in the table that process safety is expensive in comparison with occupational safety. So you can't expect an unlimited budget. Okay, it will not be reasonable to have an unlimited budget. However, under-resourcing is a risky business, so you should lay in the middle. And at last, the physical resources such as equipment, buildings, offices, rest facilities, and so on. I believe this is clear. Let's move up to criterion number 5, the setting of objectives. If you're not measuring, you're not managing. So you should have clear and effective set of short-term and long-term process safety objectives. These objectives must be SMART, which means specific, measurable, achievable, realistic, and time framed. These objectives also should be done in consultancy with employees. The management shouldn't go on its own and set these objectives and enforce the employees to achieve it. No, this is not a healthy PS culture. We are talking about the involvement of employees, so the employees should be involved. So how do I know that my objectives are effective, or how do I monitor the progress achievement of my process? You should set what is known as KPI, or key performance indicators, and we will discuss this in detail in module number 3. Okay, moving up to the last criterion of process safety management leadership, the commitment towards continuous improvement. As you know, any management system contains the cycle PDCA, Plan, Do, Check, Act. So you need to actively monitor your safety performance. The active performance measurement or active performance monitoring should be done throughout the benchmarking or throughout the auditing process. You will find where you are exactly, or where your system is exactly, and hence you will do whatever means is necessary to rectify and to assure continuous improvement of your system. I believe now we have finished the criteria of a healthy PS leadership, and now the module or element number 1 is now completed. Stay tuned for element 2. Hello and welcome to element number 2 of the process safety management system. At this element, we will discuss the process safety information in detail. So let's hop aboard. What is meant by the process safety information, or what is the definition of process safety information? Process safety information is a set of written compiled information which concerns process CTE. And CTE is an abbreviation for chemical, technology, and equipment. So C for chemical, T for technology, E for equipment. On the next slide, I'm going to set some examples of process safety information. So let's go ahead to the next slide. Regarding the chemicals, we have the Standard Material Safety Datasheet, or MSDS for short. Also, we have the chemical analysis of multi-phase stream. Regarding the technology, we have the block flow diagram, process flow diagram, process chemistry, maximum intended inventory, safe parameters, evaluation of the consequences of deviations, also known as the worst case scenario evaluation. And regarding the equipment, we have the material of construction, the P&IDs, or piping and instrumentation diagrams. We have the electrical classification, we have the relief systems and design basis, we have also the ventilation systems design, the design code and standards, the material and energy balance, and at last we have the safety systems, which are the interlocks, detection, or suppression systems. We are going to illustrate some of these examples on this element. So let's start by the chemicals. As you can see on this slide, we have 16 components of a standard material safety datasheet. The source of these elements or these components is OSHA 1910.1200. This is the standard which sets the requirements for a standard MSDS. Okay, OSHA PSM stated that it is mandatory to have, at least in the MSDS, the following components. Let me just get my laser pointer. Okay. OSHA said, or OSHA PSM said, that we should have element number 6, which is the accident release measures. Element number 8, the exposure control measures. Element number 9, the chemical and physical properties. Element number 10, stability and reactivity of the material. And element number 11. Okay, so 6, 8, 9, 10, and 11. Why these components or these elements are mandatory to be existing in any MSDS? Because they are so relevant to the trend of process safety management, which is the prevention of major accident hazards or major accidents such as fires, explosions, levies, toxic gas releases. So it is very substantial for any MSDS to have accident release measures, exposure control measures, chemical and physical properties, stability and reactivity of the material, and toxicity information. I hope this is clear. Let's move on. Regarding the technology, we will discuss the block flow diagram, the process flow diagram, process chemistry, and evaluation of consequences of deviations. So let's start with the block flow diagram. What is the block flow diagram? It is a simplified diagram showing major process equipment and interconnecting process flow lines. It also demonstrates information about flow rates, stream composition, temperature, and pressure. But please be advised that these informations are not forcibly existing in all PFDs. So don't expect to have much of information about the flow rates or stream composition. It's not mandatory to have it, but it is mandatory to have all the major process equipment existing and also the interconnecting process flow lines. So let's use this BFD as an example. As you can see, the toluene here is going as a feed with hydrogen gas. The flow rate of toluene is 10,000 kilogram per hour, while the flow rate of hydrogen is 820 kilogram per hour. They go inside the reactor. The outcome will be the effluent, which goes to a separator, at which the gas is separated from the liquids. The gas goes up with a flow rate up to 2,610 kilograms per hour, while the liquid is going to a distillation tower, at which the benzene is extracted with a flow rate of 8,110 kilograms per hour, while the recycled toluene goes back to the reactor as a feed. So, in other words, it's just a preliminary diagram which demonstrates generic information about the process. And also, please be aware that the block flow diagrams is also used as an input in the hazard identification studies or hazard studies, because hazard studies doesn't require that much level of detail, unlike other risk assessment studies such as hazard. Okay, let's move on to process flow diagrams or PFDs. Here we have a more complex diagram which shows all main flow streams, including valves. Also, it shows pressures and temperatures on all feed and product lines. Also, it shows the points of pressure and temperature control. It gives us also information about the construction materials, pump capacities, compressor horsepower, vessel design pressure, major control loops, etc. So it gives you more detailed, more rigorous, more complex information about your process, unlike BFDs. And here is an example for it. This is an isobutane reactor unit. You will see that the level of detail in this PFD is more advanced, more rigorous. It has also some additional information about the pressures and temperatures. I will attach this PFD in the course reference material. Okay, let's move on. Let's go to the process chemistry. What do we mean by process chemistry or process chemistry information? Process chemistry information means information about the type of the facility, whether it is upstream, midstream, downstream, you name it. Also, it gives us information, or it means information about the sorts of operations running inside, the types of chemical reactions and interactions. So, such information could be provided in the form of philosophy of operation, basis of design, design concept, whatever the name of the document is, it should provide the above mentioned or the previously mentioned requirements. So, in other words, the term process chemistry entitles to give you details about what is being processed in the plant and how is it done. Okay, hope it's clear. Let's move on. The evaluation of the consequences of deviations. What is deviation? Or what is the definition of a deviation? A deviation is something which will go wrong or an outcome that is undesirable. So I need to evaluate the outcome of this undesirable event. How do I do that? Or how do I define the consequence of deviations? The answer for this is pretty simple. We can use a technique called what-if technique. And this technique will evaluate what will be the outcome if a deviation from the safe operating limits takes place. The what-if technique will be illustrated later on element number 3, but let's focus on what we have right now. This evaluation will give us a rough assessment of the worst case scenario which may occur in the plant. And also you can use a software such as Aloha. This software is developed by EPA and you can download it for free on their website. This software will give you a simulation or an estimate of the threat zone for fires, explosions, toxic gas releases, or levy. But please be aware that this software is dependent upon knowing or having the maximum intended inventory, operating parameters, and others. Others include the wind speed, wind direction, the pipeline diameter, and so on. Okay, so in the process safety information element, you need to evaluate the consequences of your deviations or of the deviations which may take place alongside the life cycle of the plant. I hope it's clear. Let's move on. Now, enough talking about technology. Let's move on to the equipment. And here we are going to start with the material of construction. And I have a question in mind. Why should I have to know the material of construction for vessels, piping, or any conveying medium? Why? I will give you for this 10 seconds, then I will provide an answer. There are two reasons why should you know the material of construction for any vessels, piping, or conveying medium. They are: one, to assure the physical compatibility of it with the nature of operation running in place in terms of pressure, temperature tolerance, strength, stress, corrosion resistance, etc. And also it should consider the upsets in operation which already can happen frequently or more often. The second reason would be to assure the chemical compatibility of it with the conveyed medium, and this is done to prevent undesirable reactivity hazards. So, in other words, you should know the material of construction of your vessel, piping, or conveying medium in order to assure the physical compatibility and the chemical compatibility. Okay? Let's move to item number 2 in the equipment, piping and instrumentation diagram. This diagram is the higher level of detail in comparison with the process flow diagram. It contains all the information listed in the PFD, plus it describes the relationships between equipment and instrumentation, as well as other relevant information that will enhance clarity. So if you have a pyramid of detail regarding the process itself, you will start with the block flow diagram, and upper of it, you will have the process flow diagram, and on the top of the pyramid, you will have the piping and instrumentation diagram. The next slide, I'm going to show you an example of it. This is an example of a typical big launcher. As you can see here, the level of detail is much more advanced, much more rigorous. You will have different types of valves, vents, flares, kicker lines, and instrumentation, pressure transmitter, whatever it is existing, and it is very, very detailed, as you can see. Okay, so how do I know all of these symbols? This is a very important question. How do you figure out what does this symbol mean? A quick tip for you, there are two standards that you can use to identify the symbols stated in the P&IDs. You can use the ISO 14617-6 or you can use the ANSI ISA 5.1. These are internationally recognized standards. You will find most of the symbols of the P&IDs within it. You will have a better knowledge about all of them. But be aware that the legend symbols of the P&IDs may be referenced or custom tailored, and I mean here that the company may have a custom designed or custom tailored symbols that she or the company itself, I mean, chose to put it as a symbol on the P&ID. So be aware of that. The advice for you is to seek the legend first, if available, before diving into standards. I'm just giving you a quick tip. Okay, let's move on. The electrical classification. 3 areas here should be covered about the electrical classification. Number 1, the hazardous area classification. Whether it is zone 0, zone 1, zone 2, you should know the hazardous area classification and the basis of classification. And the best standard that you can refer to is API Recommended Practice 505. Number 2, the electrical classification, the electrical equipment classification. And here I recall the standard IEC 60079, API Recommended Practice 500, or ATEX European Directive. Okay? And number 3 is the ingress protection level of equipment. And please seek the standard IEC 60509. This will give you much better information about the ingress protection. So, in short, you should cover the 3 areas of hazardous area classification. You should know the classification of the plant or the area classification of your plant. And consequently, you should have a clear knowledge about the electrical equipment classification and the ingress protection in relation to environment. You will need such information for later use. Don't forget to have the datasheet for such equipment. This is a friendly advice. Forget that it is red tagged, but it is a friendly advice. Let's move on. Relief systems and design basis. You need to have a documented copy of the plant design basis for the following purposes. Number 1, to identify the foundations of the design and relief systems. And 2, to see through the relief systems and compare their set points to the operational limits of units. This is a very important and very critical information that you must have. At last, you should assure the conformity of these relief systems with internationally recognized standards. And here I recall the API standard 520, 521, and 2000. These are the best standards for relief systems. Okay? This table also gives you a clear view of most of the European standards and international standards that talked rigorously about the relief systems. I will attach this table in the course resources. You can get it if you want and dive through the standards. Okay, moving on, we will discuss the ventilation systems design, and here I mean the enclosures, such as a power plant enclosure, switchgear enclosure, and etc. You should have the following information. Number one, the functional description of the ventilation system. You should know the description of the ventilation system, the fan control, alarm signals, normal versus emergency ventilation, and so on. Number two, you should know the fan specifications in terms of airflow, pressure, motor type, blade material, room characteristics, dimensions, volume, makeup, air dampers, design basis, code or standard to which the ventilation system was designed to. And here I recall the best standards regarding the ventilation systems, which are the NFVA 30 and NFVA 58. Okay, moving on. The design code or standard. As part of any process safety information, you should know the design code standard of manufacture or testing or maintenance or inspection of all equipment within the facility. This will give you assurance of the compatibility of use and maintenance of such equipment. Be aware of that. As we discussed, if you recall, the material of construction, I said that we must know the material of construction in order to assure the chemical compatibility and physical compatibility. However, now on the design code or standard, you should know it all in order to give you assurance of an overall compatibility for use and maintenance. Okay, moving on, let's talk about material or energy balance. Material or energy balance is a statement of the conservation of mass or energy as the material quantities pass through processing operations. In other terms, what goes in as a mass goes out as a mass, or what goes in as an energy must go out as an energy, provided that nothing changes. Okay? From this example, let's implement the law of conservation of mass, which was invented by Antoine Lavoisier, and the law of conservation of energy, which was developed by Bernoulli. If you see this graph, we will have that mass in, which is here, equals mass stored plus mass out plus waste product or mass waste. So mass in should be equal to all of these three elements. While energy in, as you can see here, which is energy in heat, work, chemical, electrical, whatever, must be equal to energy stored plus energy out plus energy in waste plus energy lost to surroundings. The importance of these calculations is that it will give us necessary information about all inputs of mass and energy in the operation. Number two, you will be able to identify if there is anything wrong in the processing operation. For example, if you find an imbalance in the mass or energy, you can start investigating the cause of such imbalance. For example, if the mass here is not equal to the summation of this, or that the product itself or the mass out is less than expected, you will start investigating the cause of such waste. And the same goes also for energy. Okay, let's move on. We will talk at last about the safety systems, which are the interlocks, detection or suppression systems. Let's start with the safety interlock. The safety interlock is a feature that makes the state of two mechanisms or functions mutually dependent, which means that one mechanism cannot start without the presence or activation of another mechanism. A simple example of this is the safety pin, which is existing on the fire extinguisher to prevent the extinguisher from being mistakenly or accidentally used. You will have to remove the pin first and use the extinguisher. So this pin acts as a safety interlock. The safety pin also for the pistol or the gun, it acts to prevent the gun or the pistol from being used or accidentally fired unless you unlock this safety pin. Okay, so we have types of safety interlocks such as the trapped key interlock, microprocessor interlock, mechanical interlock, electrical interlock. Just know the names. You don't have to memorize anything. I'm just setting some simple examples. What about the safety detection systems? It includes any device that is able to detect process upsets or undesirable safety events. So we are talking now about two layers of protection: the basic process control system protection layer and the fire and gas detection system protection layer. Okay, this includes the over pressure, over temperature, over speed switches or sensors. Number two, the fire and gas detection systems. The fire suppression systems. It includes deluge rings, water sprinklers, chemical agents, total flooding agents such as the FM200, Energen CO2, etc. And also many more, of course. So what do you need to know regarding the safety systems? You will need to know the specifications of the system, the location of the system, the quantities of the units used in the system. Number two, the basis of selection for these systems, references and standards if applicable. Number three, you will know the hydraulic and demand calculations of the suppression system to make sure that it covers the threat area. And at last, you'll have to know the types, basis of selection, allocation of fire and gas detection systems, and to assure the suitability of them to the process type. And remember, if the process safety information listed in element 2 is not or partially available, do not proceed to element number 3 unless you fulfill them, because element number 3 depends on element number 2, and if element number 2 is not available or partially available, you will not have a successful or active or effective element number 3, which is the process hazard analysis. You will not be able to do a correct or effective or accurate process hazard analysis unless you have appropriate inputs. And in the end of this element, I hope you all gained the best benefit out of it. And please do not hesitate to leave your comments or questions in the course discussion board. Stay tuned, guys, for element number 3. So hello and welcome to element number 3 of the process safety management system. This element will discuss the process hazard analysis, and I consider it as one of the most important, yet the most critical element of the whole process safety management system. So let's get started directly. What is the meaning of process hazard analysis? Okay, the definition of process hazard analysis is an organized and systematic set of techniques to identify and analyze the significance of potential hazards associated with the processing or handling of highly hazardous chemicals. So, basically, the process hazard analysis is a combination of techniques or a set of different techniques which are used to identify and analyze the significance or the importance of potential hazards associated with processing and handling of highly hazardous chemicals. Okay, the PHAs, which is a short of process hazard analysis, analyzes potential causes and consequences of fires, explosions, releases of toxic or flammable chemicals, and major spills of hazardous chemicals. So, as you can see, it is very important and very critical element of the PSM system. Okay. So, what does the PHA focus on? Sorry. The PHA focuses on equipment, instrumentation, utilities, human actions, routine and non-routine, and last, it focuses on external factors such as the surrounding environment. Okay, but before we go in depth about the PHA techniques or the PSM related PHA techniques, let's have some definitions regarding the hazard, the risk matrix, the categories of PHA, the risk criteria, the tolerability of risk, the PHA team, main stages of PHA process, and the key elements of a high quality PHA. So you need to be familiar with all of these definitions, okay, before we get into depth regarding the PSM PHAs. Okay, so let's get started. What is a hazard and what is a risk? What is a hazard and what is a risk? The hazard is anything which has the potential to cause harm or loss of any type. Such harm or loss could be injury to people, damage to equipment, or any environmental harm. While the risk is the combination of the likelihood of the hazard to occur and the severity of that harm. So it is the outcome of the likelihood, which is the probability or frequency, times the severity, which is also known as the consequence. Okay? Okay, what about the risk matrix? What is the risk matrix? The risk matrix is a tool used in the PHA process to define the level of risk. It is used to give you a clear definition about the level of the risk, considering both probability and severity. As you recall from the previous slide, we said that the risk is the combination of the likelihood, which is the probability of the risk, and the severity, which is a consequence. So the risk matrix considers both probability and severity, and thus the matrix itself can be qualitative, semi-quantitative, or quantified, and we will get to this on the next few slides. Okay? We must also know that the risk matrix considers four major affected elements, and they are, on the gathered word, MEEP. MEEP is short for material, equipment, environment, and personnel. So remember the word MEEP. The company can use internationally recognized metrics or it can use its own depending on availability. And it's better off to use the companies because you'll know it better and you will have a clear definition of risk criteria. So let's see some examples regarding qualitative, semi-quantitative, and quantitative risk matrices. So this is an example for a qualitative 5 times 5 risk matrix. As you can see here, both the probability and the consequence of the occurrence for the hazard are expressed in the terms of ranges. It can be low, it can be moderate, it can be high or excessive. So there are no numbers involved in this type of risk matrix. Okay, moving on. This is the semi-quantitative 5 times 5 risk matrix. As you can see here, the numbers are beginning to be introduced in terms or in addition to the ranges, and the numbers, of course, mean something. This thing will be referred to in the risk criteria, and this is another subject that we will go to further on our program. At last, we have the quantitative 5 times 5 risk matrix. And here, there are no ranges. If you can see the probability, which is the likelihood level, and the consequence, which is the severity level, they are all expressed in numbers. And these numbers, of course, also, same as the semi-quantitative risk matrix, are referred to the risk criteria. So remember the risk criteria because they are the basis of your selection to the likelihood level and the consequence level. So PHAs accordingly will be qualitative, semi-quantitative, or quantitative. In the qualitative risk assessment or PHA, the frequency and severity are determined purely qualitatively, which are the low, medium, and high, same as the risk matrix, while the semi-quantitative, the frequency and severity are approximately quantified within the ranges of low, medium, high, while the quantified pure numbers, and we said it before in the risk matrix. So now we are going to move on to the risk criteria. The risk criteria here is very, very critical in the PHA process, as the definition of risk criteria must be done before conducting any sort of PHA. Okay, because the definition of risk criteria will provide you with a suitable enumeration or for all elements of the risk matrix, and I'm talking here about the consequence and the probability. Okay, so the risk criteria is dependent upon four major factors. First, you should set the scale impact qualitatively or quantitatively. Second, you should define the tolerability framework, and we will come to this on the next slide. Whether the risk is broadly accepted, alarm, which is as low as reasonably practicable, or intolerable risk, and you should define them all. Okay. Third, you should define the method of expressing the probability. And at last, you should define the type and nature of consequences. And I will attach a document which serves as a very good guide for defining the risk criteria. Okay, moving on. Let's talk about the tolerability of risk framework. We have three types of risks categorized according to the level of tolerability. Number one is the broadly accepted risk. And this risk means that there are no further measures needed in order to further control the risk. And this is generally concluded in a qualitative PHA. And this broadly accepted risk doesn't require anything else. You will identify it and you will find that the existing control measures are more than enough to control the risk. Therefore, no additional control measures are needed. Okay. However, please be aware that you are the one who is defining the criteria for broadly accepted risk, if you recall from the previous slide. Okay, moving on to the second type or the second category, we have the as low as reasonably practicable risk or alarm risk. And here, more rigorous assessment is needed to further control the risk within reasonable tools such as semi-quantitative or quantitative tools, but here we prefer the semi-quantitative risk assessment or PHA tools. Now, things are starting to get more advanced or more complicated. The existing control measures are not enough to contain this risk in the boundaries of broadly accepted region. Now we need additional control measures, so we should use more advanced, more detailed tools for risk assessment or PHA. That's why we should use the semi-quantitative or the quantitative methods. And regarding the level of risk reduction, we should reduce the risk to a point that further reduction will be grossly disproportionate in relation to the cost. You cannot spend so much money in order to control the risk. You have to be also playing in the middle. As you recall, regarding the provision of adequate resources, we cannot expect an unlimited budget and we cannot tolerate under-resourcing. Okay? And here we have the third category of risks in relation to tolerability, which is the intolerable risk. And here the risk cannot be contained in the broadly accepted region, of course, and the alarm region. So you need to quantify the risk in order to have a full picture. And but what I mean with the full picture is that you will need to transfer the findings to top management in order to provide adequate or more resources for further control of the risk. Now, let's take an example. I have made my risk assessment, a semi-quantitative risk assessment, for a specific hazard of overflow from the tank. Okay, and on the semi-quantitative risk assessment findings, I found that the risk will be intolerable. Why intolerable? Because the existing control measures are not enough. So I need additional control measures to reduce the risk. However, I need more money in order to do that. So how do I transfer or how do I show the management that I really need additional resources? This cannot be done appropriately unless you give them numbers that they agreed on the risk criteria that this will be my intolerable region. Remember this. That's why I told you that the risk criteria must be defined by the company or preset by the company. Okay? I hope this is clear. Let's move on. Let's talk about the PHA team. The team should be competent enough to be grouped in PHA team. And by competent, we mean that the members of the team should have enough knowledge and ability and training and experience. This is very important, very critical. OSHA mandates that at least one employee with experience and knowledge about process being evaluated should be in the PHA team. So this is logical and nothing more to explain. OSHA also mandates that at least one employee familiar with the PHA technique should be also in the group. Okay, and I need to remind again that incompetent PHA team will lead to poor and unreliable PHA results. Okay, so let's move on to the stages of PHA or any PHA. The main stages for any PHA process consist of the following. The first step will be the hazard identification. You should identify what are the hazards that are presumably existing or could exist. Number 2 will be the risk estimation and ranking of risk. Number 3 will be the risk evaluation and implementation of risk reduction measures. And at last, we will have the review. And the review aims to identify additional control measures that can further reduce the risk. And this happens frequently in the intolerable risk region, of course. So, what are the key elements for high quality PHA? Just remember the 5 T's. The 5 T: team, technology, training, tools of analysis, and time. You should have a competent team. You should have the right technology for documentation. You should have a team with appropriate training, and you should use the appropriate tool of analysis. And at last, you should provide adequate time for performing the PHA. So now we are going to talk about the types of PHAs stated frankly in the standard of OSHA PSM. We have basically 5 types that were enlisted directly in the standard. They are as follows. We have number 1, the hazard and operability study, also known as HAZOP. Number 2, we have the failure mode and defect analysis, also known as FIMIA. Number 3, we have the fault tree analysis, FTA. Number 4, we have the checklist. And number 5, we have the what-if checklist technique. OSHA said also that other equivalent methodologies are accepted as long as they serve the same purpose. Okay, so let's agree on that. On the next slide, I'm going to show you some equivalent methodologies that I believe they serve the same purpose. For example, we have the root cause analysis, cause-consequence analysis, cause and effect analysis, scenario analysis, failure mood and effect and criticality analysis, which is known as FIMICA. And please remember the last one because we are going to refer to it later on. So, on the next slide, we are going to categorize the types of OSHA, PS, and PHAs. Let's go directly to the categorization. If we are going to classify the types of OSHA, PS, and PHAs, then we will come to the following conclusion. Checklists are considered to be as a lookup method to the process itself, while supporting methods are like the what-if checklist technique, and the scenario-based analysis is like the fault tree analysis, and the function analysis is like FIMIA and HAZOP. So this is just a categorization. It's based on the standard ISO 31010. It's just giving you a general framework. What is the general classification of the listed types of PHAs? So let's move forward and we shall start. Let's go by the hazard and operability study, which is known as also HAZOP. It's a thorough, structured, systematic, team-based guideward examination of process or system to identify hazards in relation to process deviations, along with the provision of suitable control measures. So, what are the process deviations? Generally, there are 4 basic deviations, which are any change either by increase or decrease in pressure, temperature, flow, or composition of the gas itself or the stream itself. And the best reference that you can get to in order to have a more detailed information regarding HAZOP is IEC 61882. This standard or this recommended practice will give you a very, very detailed guidance regarding the implementation and the actual carry out process of the HAZOP. The HAZOP can be qualitative, as we mentioned before, if you recall, or semi-quantitative, according to the type and appetite of the management. And also, I would like to say that it is qualitative or semi-quantitative according to the level of risk as per the tolerability classification. If you recall, we have the broadly accepted risk, and we have the alarm risk, and we have the intolerable risk. So if I am diving through the broadly accepted risk region, so there is no need to go to a semi-quantitative analysis. However, if you started with a qualitative HAZOP assessment, and you found that some risks were found to be in the alarm region, so you must go to the semi-quantitative technique of HAZOP. Remember that HAZOP is a cause-based thorough analysis, so the assessment is cause-defined or cause-based. Let's go to the technique of HAZOP. First, let me just get my laser pointer. First, the P&IDs is broken down into small sections called the nodes. Second, each node will have a parameter or more to be examined. The parameter, as we said before, will be temperature, pressure, flow, composition, or whatever you choose to select. It's not mandatory to have these 4 parameters all the way the life cycle or all the way the assessment process of HAZOP. No, you can just select other parameters and seek through step number 3, which is you will have to select a guide word, and this guide word is agreed to be combined with the parameter in order to form a deviation. So first, you will have to establish the parameter itself, and the basic process parameters are temperature, flow, pressure, and composition. However, These are only parameters. If you add more flow, more pressure, less pressure, this guide board added to the parameter will form a deviation. Number 4, the PHA team will analyze the potential causes of this deviation. What is the cause of increased pressure on this segment, and so on, and so on. And what is the cause of low pressure in this section, and so on. Eventually, they will put the control measures. Okay, so this is in brief the technique of HAZOP. I would like just to say that the most important process safety information for the HAZOP is the P&IDs. Okay, you must not start the HAZOP without a valid, verified, and as-built P&ID. Okay, let's move on. After the HAZOP sheet is finalized, a closeout report must be issued with the required actions and recommendations for active follow-up and monitoring. Okay, of course, I'm coming out with recommendations and existing plus needed control measures that must be documented in the closeout report. The final sheet will look like this. We are just taking one parameter, that such as the temperature. We have our guide word here, less, we can choose more, however. So combining the guide word with the parameter, we will have our deviation, which is less temperature. We need to identify the cause of less temperature, let's say more cold water flow. Okay, then what will be the consequence of this deviation? It will be discomfort, for example. So I am multiplying the probability of the cause with the consequence of that effect if it happened. Then I will have my risk ranking, let's say medium. So what is the action or the existing or the needed safeguard? We will have a thermostat valve which will handle. Okay? Okay, let's talk about the limitations of HAZOP. The HAZOP is a detailed analysis. And by detail, we mean that it will be very time consuming and therefore it will be expensive. Such detailed analysis will require a high level of documentation for the system or process and procedure specification. Also, HAZOP can focus on finding detailed solutions rather than focusing or challenging on fundamental assumptions. For example, what if the equipment itself failed? Because the HAZOP doesn't assume that the equipment, which will be the safeguard or the control measure for the deviation, fails. It assumes that it is operational and it is healthy all the time. So HAZOP doesn't challenge fundamental assumptions. Okay? And at last, we have that the discussion of HAZOP can be focused on detailed issues of design and not on wider or external issues, okay, such as environmental aspects and so on. I know that what I provided is only a brief introduction about the HAZOP because if we are going to talk about it, it needs a complete course. I'm just giving you a brief about what is HAZOP and how the technique of HAZOP is done. I'm trying to provide you just a glimpse about the true meaning or the academic meaning of HAZOP. Now let's talk about the failure mood and effect analyses, or also known as FEMIA. What is the FEMIA? The FEMIA is a technique used to identify the ways in which components, systems, or processes can fail to fulfill their design intent. So what is the definition of failure? Okay, the failure is the loss of ability to perform as required. Simple as that. Okay, the failure is the loss of ability to perform as required, or it is an event that results in a fault state of that item. And there are several types of failure. They are according to consequence: catastrophic, critical, major, minor, marginal, insignificant. And according to cause, it may be misuse, mishandling, weakness, etc. Okay? And the best standard that you can refer to in order to have a more detailed information or more detailed guidance regarding the FEMIA is IEC 60812. Okay? Moving on. The FEMIA identifies all potential failure modes of various parts of the system. Number 2, the effects of these failures may have on the system. Number 3, the mechanism of failure itself. And number 4, how to avoid the failure or how to mitigate the effects of these failures on your system. From the terminology itself, we have the failure, we identify the failure. Number 2, we identify the mode or the type of the failure. Number 3, we see the effect of that failure on our system. And number 4, we make the analysis to study the risk in order to reduce it or eliminate it if possible. On the next slide, we are going to show you some popular types of FEMIA. We have the design FEMIA, process FEMIA, service FEMIA, software FEMIA. We are going to focus on the process FEMIA. Moving on, we will go to how to do the FEMIA technique. As you can see from this graph, we are starting by identifying the failure mode itself. Okay? Following after the identification phase, let me just get my laser pointer. Following after the identification phase, we see the effect, or we identify the effect of that failure, which is what will happen as a result of that failure. Number 3, we will identify the severity, how severe the impact is to the user or the customer or to the process. Okay. Number 4, we shall identify the cause of such failure. Okay. Number 5, we will see the occurrence or the probability or the likelihood of the occurrence of such failure. Number 6, we will see something which is called as the detection mode. Okay. And by detection mode, we mean that we need to define what controls are currently in place to spot such failure before it happens, or detect it after or if it happens. Okay, so the detection mode is what controls are currently in place in order to spot the defect before it happens or when it happens. Okay, following that, we will see the detection itself, which is the probability or the likelihood of such failure to happen or to take place without it being detected. Okay, we are seeing the probability of that failure to reach the state that it will happen without it being detected. Afterwards, we shall deduct or we shall conclude the RPN. The RPN is the risk priority number, which is the result of multiplying the severity with the occurrence. Okay, which is in other words the risk. As you recall, when we said the risk is the combination of the likelihood of the event to take place and the severity of that harm. So the RPN is the result. Finally, you are getting to the stage that you need to take action if the present control measures are enough or you need additional control measures. Okay, the risk priority number gives you the priority, which action should take place first or which failure mode should take place for actions first, and that concludes the FEMIA technique. Following that, here you can see the sheet, a typical sheet of FEMIA. We see here the description, okay, description of the system under process. And here we go to the potential failure mode, the effect of that failure, what are the causes of that failure, okay. Then we have the assessment of the severity and occurrence and detection, okay. The combination of the severity with the occurrence will be the RPN number, okay. So the countermeasures are taken, who is responsible, what is the action, and what is the due date. Then you calculate the residual risk or the residual RPN. The severity will reduce after the implementation of this countermeasure. So as the occurrence and detection, I believe you will have a lower RPN numbers. And same as the risk criteria, which were set by the management, they should also do that for FEMIA. They should give a quantitative matrix of the RPNs, which are in the broadly accepted risk region or the alarm region or the intolerable region. Okay, so we have another importance or another significance of the RPN beside giving the priority to actions is to give you an insight about the potential or the level of that risk. Okay, here we have a notice that when actions are taken for the higher RPN failure modes, okay, you should recalculate it. So if I'm having a high RPN number before setting the countermeasures and a high RPN number after setting the countermeasures, I should do more assessment. I should implement more countermeasures in order to reduce the residual RPN number. So I believe I gave you an insight about the technique of the FEMIA. Let's talk about the limitations. Number 1, they can be used only to identify single failure mode. You cannot combine multiple failure modes together. Number 2, unless adequately controlled and focused, the studies can be time-consuming and costly, same as the HAZOP. Number 3, they can be difficult and tedious for complex multi-layered systems. As we said in the first limitation, that they can be used only to identify single failure mode. How about studying complex multi-layered system? I believe it will be difficult. So this should conclude a brief insight about the FEMIA. Let's move on. Now we are going to discuss the fault tree analysis, or FTA for short. The fault tree analysis is a technique used for identifying and analyzing factors that can contribute to a specified undesired event, which is called as the top event. So it identifies and analyzes the factors which will contribute or can contribute to a top undesired event. The causal factors are deductively identified, organized in a logical manner, and represented in a tree diagram. That's why they call it the tree analysis. And this tree diagram depicts the causal factors with their logical relationships or relationship to the top event. The FTA is considered to be the best alternative to FEMIA. As you recall, in the previous slides, we said that the FEMIA cannot discuss combined failure modes altogether. However, the fault tree analysis can do that. That's why it's a good alternative for discussing combined factor of failures altogether. The FTA can be qualitative or quantitative, and I prefer the quantitative method to be discussed or to be used in the functional safety assessment for safety integrity level or cell determination, and this is another topic, of course. The best standard that you can refer to in order to have a more detailed information or detailed guidance about the FTA is the IEC 61025. Okay, just remember that the fault tree analysis follows the top-down approach. Okay, so now let's discuss the technique. As we said that the FTA follows the top-down approach, so we have here the top undesired event. What are the causal factors of this undesired event? We will have here an intermediate event number 1 or the intermediate event number 2. Any one of them will be inserted in the logic gate of OR. This is a symbol for a logic gate of OR, okay, to the top undesired event. Okay, what causes the occurrence of this intermediate event number 1 or number 2? It can be a basic event number 1, and this is the logic gate of and the basic event number 2. So the basic event number 1a and the basic event number 1b will give rise to the intermediate event number 1, okay? And the basic event number 2a and the basic event number 2b will give rise to the intermediate event number 2. The intermediate event number 1 or the intermediate event number 2 could give or will give rise to the top undesired event, okay? Here we have this diagram or this assessment. Let's zoom in. So here we have the failed automatic startup of emergency generator. What will be the causes? We have here a diesel generator fault or no startup signal. This is the gate of OR. I believe if we came here to the symbols, this is the OR gate, okay? What causes the diesel generator fault? It could be a mechanical fault in the generator, or it could be due to lack of fuel, okay? So what causes the lack of fuel in the generator itself? It could be due to absence of fuel or blocked intake. This is the OR gate, okay? Let's take the other branch. We said here that there are no startup signals, or there is no startup signal. What are the potential causes of no startup signal? It could be a fault in the sending signal. It could be a fault in the transmission of signal. It could be the fault in the reception of signal. And this is the OR gate. So these are 3 different reasons or 3 different causes. Following that, what could be the cause of a fault in the transmission of signal? It will be due to a broken conductor, while the fault in the reception of the signal could be due to a fault in the control module, and the fault in the control module will be due to a fault in the circuit A and a fault in the circuit B, and this is the AND gate. I believe it's clear. So I've given you a practical example of a fault tree analysis. Let's move on to the limitations of fault tree analysis. What are the limitations of fault tree analysis? Number 1, uncertainties in the probabilities of base events are included in calculations of the probability of the top event. And this could result in a high levels of uncertainties where base event failure probabilities are not known accurately. However, a high degree of confidence is possible in a well-understood system. Okay? Number 2, in some situations, causal events are not bound together. You cannot insert AND gate or you cannot insert the OR gate. Okay? And number 3, fault trees can only deal with binary state failure or not failure only, okay? Number 4, fault trees is a static model. Time interdependencies are not addressed, and here we are talking about failures over time. Number 5 will be that human error modes cannot be easily included. You cannot just say that human error is a part of the causal factors to the base events. It cannot be easily included because you're assuming that this human will do his job as required. And at last, it doesn't enable the domino effect, such as in bow-tie model, and we will talk about the domino effect in the incident investigation element. So I believe this is all of the fault tree analysis. Let's move on. Now we are going to address the checklists, and this is an easy one. Checklists is a list of hazards, risks, and control measures or control measures that have been developed usually from experience, either as a result of a previous risk assessment or as a result of past failures. How are we going to create this checklist? First, we need to identify or define the scope of activity. Second, the checklist is selected, which adequately covers the scope that you have defined. That last, the team uses the checklist steps through each element of the process or system and reviews whether items on the checklist are present or not. Okay? Let's move on. This is an example of a standard checklist. You can see here it's talking about a tank. The tank size, tank serial number, you insert all of these data together and you check the status or the elements that you need to see through, and it's only a yes or no checklist. What are the limitations of checklists? I believe they tend to inhibit imaginations and identification of risks. Of course, you have either yes or no, you have a predefined scope. All what you have to do is just tick the box, nothing more. Number 2, they address the known knowns and not the knowns unknowns or the unknowns unknowns. And here I mean that it's based on experience, it's not based on brainstorming, so you cannot assume that additional risks or additional control measures are present. It doesn't encourage you to do this. And number 3, they encourage the tick the box behavior. Number 4, they tend to be observation based, so miss problems are not seen. Okay, At last, let's go to the structured checklist, or what if. This is a combination of the checklist and what if technique of the PHA using a defined, detailed, and structured approach. Okay, so you are combining the acquired knowledge or experience through the checklist with the brainstorming of the what if. You will have the structured what if checklist. So the structured checklist what if combines the best aspects of HAZOP and FEMIA with the power of brainstorming. Number two, it can be used to look at the system from any angle without any restriction of structure. Number three, it's better used for identifying issues outside the boundaries of other studies. Okay? It's easily understood, of course, and can be used for less experienced users. And it is more rigorous assessment than HAZOP and FEMIA. So let's talk about the technique. Step number one, you generate a process variable deviation questions, okay, such as what if the flow is too high or too low, okay. Number two, you generate the failure mode questions for each component. This step is the cause identification step, as at which you will discuss the failure mode questions, such as what if the flow transmitter fails with a false high flow indication. You are now combining the techniques all together. Number three, you generate other questions using checklists, and this is done by experience. And at last, you generate other questions using brainstorming. So you have combined it all together. You have listed the process variable deviations from the HAZOP. You generated the failure mode questions from FEMIA. You used the checklist to generate questions. And at last, you used your brainstorming or the brainstorming of the PHA team to generate other questions. Okay, what are the limitations of checklist what if analysis? It requires, of course, a great deal of focus on specific parts of the process in order to avoid scattered approach. Okay. Number two, it requires a lot of discipline not to take shortcuts, because if you recall here, there are several steps. You should go through them respectively, so you shouldn't take any shortcut, and this is very important, and that's why it requires discipline. Okay, I believe now we have finished all the listed or required PHA techniques by OSHA PSM standard. Let's move to the applicability of techniques for PHA. So now, let's go directly to the applicability of techniques for PHA. We have listed here the 5 types of techniques which were stated, frankly, in the OSHA PSM standard. And as you can see here, we've listed the risk assessment process elements regarding the risk identification, consequence, probability, level of risk, and risk evaluation. You will see here the applicability, and you will find that the structured what-if technique, along with FEMIA, are strongly applicable throughout all phases of the attributes. The source of this table is the ISO standard 31010. I will attach it to the course resources, and you can get to it for further guidance. Okay, let's talk about the attributes of selection for PHA techniques. And this is done in relation to the influencing factors, which are the resources and capability, the nature and degree of uncertainty, the complexity, and the ability to provide a quantitative output. Okay, so if you talk here about the HAZOP, you will see that it requires a medium range of resources and capabilities, and it does provide a high degree of uncertainty. It's also high in complexity and doesn't give you a quantitative output. While FEMIA requires medium resources and capability, medium degree of uncertainty you will find, and medium level of complexity, and can provide, of course, a quantitative output. The fault tree analysis require a high deal of resources and capability, and also provide a high degree of uncertainty and medium level of complexity, and also can provide a quantitative output. The checklist doesn't require a high deal of resources and capability. It doesn't give you a high level of uncertainty. It's not that complicated, and of course, it cannot give you a quantitative output. The structured what-if checklist technique requires a medium level of resources and capability, a medium level of uncertainty you will find or you will have. The level of complexity will be medium, and it doesn't give you a quantitative output. I've just listed this table in order to give you an overview about the relevance of influencing factors with the techniques stated by OSHA PSM. So, what to choose after all? I can tell you frankly that there is no magic bullet for all. You can't just use one type of PHA techniques to implement it and to go all the way with it. As we have seen in the previous slides, different types of techniques serves different purposes, so there's no magic bullet for all. You will need to combine various types of PHAs in order to cover the different aspects of the process. At last, what about the review cycle of PHA? OSHA mandates that PHAs should be reviewed periodically with an interval no more than 5 years. So at least every 5 years, you should review the PHAs that you created. I thank you so much for bearing with me in this long element. Stay tuned for element number 4. Hello and welcome to element number 4 of the PSM